Hello everyone, my name is Esther. I'm here today for a session on neural networks with Jean, and I'd like to welcome him to take us through our session. So Jean, you can start your session. Yeah, welcome.
Thanks. Hey guys, let me share the screen a bit. Yeah, I hope you can see my screen. Present. Yeah, hey, I'm Jean Salvi. I'm a software engineer based in Rwanda. Basically, I'm interested in AI and automation. So today I'm going to talk about like building your network from scratch. Basically, I'm going to take you through like neural network structure, how it works, and some fundamental idea you should have like before diving into like deep running or deep neural network, like advanced stuff in AI and machine learning. So this image is for neural network, how it looks like. Basically, it's input. If it's maybe your age, let's say maybe we want to predict a housing price, we can say like this house, how many rooms does it have, living room, bathroom, or kind of stuff like that. Is it in city or those kind of like inputs you can give it to it. That's kind of input like your network can take and like process them, try to output like one or you can like have like one output or multiple output depend on your network architecture in even like what you want to predict actually. So yeah, so I'm going to talk about the agenda of today's perceptron algorithm, zero function, softmax, cross entropy, gradient descent, NN architecture, and feed-forward backpropagation, and some demo code on artificial neural network. So yeah, let's first watch this video. This is my favorite like lecture from Udacity. So it's kind of like introduction to neural network actually.
So let's start with two questions. What is deep learning and what is it used for? The answer to the second question is pretty much everywhere. Recent applications include things such as beating humans in games such as Go or even Jeopardy, detecting spam in emails, forecasting stock prices, recognizing images in a picture, and even diagnosing illnesses, sometimes with more precision than doctors. And of course, one of the most celebrated applications of deep learning is in self-driving cars. And what is at the heart of deep learning? This wonderful object called neural networks. Neural networks vaguely mimic the process of how the brain operates, with neurons that fire bits of information. Sounds pretty scary, right? Matter of fact, the first time I heard of a neural network, this is the image that came to my head. Some scary robot with an artificial brain. But then I got to learn a bit more about neural networks, and I realized that they're actually a lot scarier than that. This is how a neural network looks. Matter of fact, this one here is a deep neural network. It has lots of nodes, lots of edges, lots of layers. Information coming through the nodes and leaving is quite complicated. But after looking at neural networks for a while, I realized that they're actually a lot simpler than that. When I think of a neural network, this is actually the image that comes to my mind. There's a child playing in the sand with some red and blue shells, and we ask the child, can you draw a line that separates the red and the blue shells? And the child draws this line. That's it. That's what a neural network does. Given some data in the form of blue and red points, the neural network will look for the best line that separates it. And if the data is a bit more complicated, like this one over here, then we'll need a more complicated algorithm. Here, a deep neural network will do the job and find a more complex boundary that separates the points. So with that image in mind, let's dive in and learn about neural networks.
Yeah, that's I think that's a good introduction to have.
So let's start with two questions.
Yeah, that's a good introduction to have actually for neural network. I think everyone like gets a pretty good idea of a neural network. So here is like a simple linear regression like neural network. You can like as the video said, you can like draw a line to separate this line. Maybe you want like this data is for like accepting student maybe in university or something. You are looking for grades and tests. Maybe he took or she took tests and grades, high school grade or something, and you want to predict if someone like get accepted or not, and you have past data. Past data is like if the student get accepted or not, depending on grade and test. So as you can see, this red line is like student who got rejected, and this blue line is for student who get accepted actually. So neural network basically what it does is drawing a line like to separate these um, this data. So I don't know if you can see my cursor, but let me try a bit to see. To see. Yeah. That's not working. So let me use this. So yeah, so basically this is the line. So as you can see, a neural network, we have to draw the line here. This is a simple neural network actually. So think of it as like a linear function actually, which like w is which is basically a weight, as you see, like the linear function wx plus b, which is equal to 0. That's a simple linear function. So if maybe x1 is grade, x2 is test. So all the grade and the test have to have like weights. It may be 0 or 1 or something like that, and bias unit, which is b. So this is a line wx plus b, and wx plus b, which is equal to 0. So we basically have to, if you want to predict if something is, so if a student get accepted or not, given like the input, which is a grade or and test. So it have to plot like the point here in this in this it have to plot the points you give it. Maybe I give it like let me see. Yeah, so it's have to print the points. I was looking for a cursor, but I guess you can see it. So it have to, if I give maybe a grade of 7 and a test of 5, so the point will be here. So depending on this, the point will be here. Depending on this line, that means this student will get like rejection. So maybe if I tweak, like I give it 9 and 7, it will have to be here. So that student will have to be accepted. That's a simple neural network does actually. So this is a line which will predict if the student get accepted given the input. So it have to return variable if it's 0 or 1. So that's basically a simple linear function you can see. So data will not always be like linear. So you may have like so many inputs coming. So like class, lang, rank, test, and grade. So This is quite more complicated, like which is not two-dimensional actually, like the one we're dealing with, because this is what two-dimension. So it's you have to come up with like which is this function which is not two-dimensional actually. Given like the input, we have to w1 w2 up to wn plus p. So which is would be mimicked from it's kind of simplified with like this vector of like w, which is weight, and x, which is vector of weight of inputs, and bias, which is pretty much equal to 0, like a very simple function actually. So a perceptron. So a perceptron is like it's kind of like a building block of neural network. So a perceptron, what does is like, as I was explaining, is like taking the input x1, x2 up to xn plus bias unity, and it we have to like draw a line here. So if depending on the input and weight and bias unit, so it have to draw a line, and this is a linear function, simple linear function. So for us to get like the final output, maybe you want to see if the student get accepted or not, it will turn yes or no. So that basically means you have to return yes or no. We have to have like a step function which is going to decide. That step function will pretty much look like this, where like you have if it will be what if wx plus b is greater than or equal to 0, or b it will be 0 if wx plus b is less than 0. So that's a step function we should have like for this simple linear perceptron. So you might be wondering like how we like our neural network actually learn. So given like the points, we have points like the data coming, the label data, that means you have data which is basically saying, okay, I have this grade, I have this I performed this in high school and I'm applying for a certain university. So you given the data, and if someone is accepted or not, that means you would know the point why you're training the data. You have data and you have the label, like the outcome you are expecting for neural network to predict. So that means like if you see this point it's in like red area, but it's supposed to be in blue area. So what this point will do is like it will say like come closer. That doesn't say it this way mathematically, but it will say like come closer to this line. So we may actually have like so many points here which are misclassified or classified well. So the classified one we have to say like you can go away. I'm okay here. You can go away. So that's the basically like linear function you have here is like, which is like this is the weight one, index one. So weight one x1 is plus 3x1 plus 4x2 neg 10, which is basically equal to 0. And given the point 1, which is not like correctly classified, so it will have like given the point 1, if we populate 1 and 1 here, that means it's 3 plus 4 negative 10, which is equal to 3 plus 4 equal to 0, which basically will give like a negative output, which means it is misclassified. So that means here to update, there is a running rate here. The rate we want to diminish some kind of error. I will get back to it later on in this session. But for now, you can think of rate like a rate that we are like how because like we can't take a step like which is a big step to come and like go below these points. We might have like so many points here which are like going to be misclassified. So that means we have to take like a small weight and see if the error is decreasing or increasing. So that basically what we did here. We take this and we add step running rate or step, and after that we got new weight and bias. As you can see, we add also learning rate with bias. So if we get new line, if we try to draw this line with this new line, that means the line will somehow come closer to these points actually. Yeah. Yeah, perceptron algorithm that basically start with random weights, x1, x2, that random weight I was using up, and for every mixed classified point, like if its prediction is 0 for n, like if prediction is low, we have to like add, and if the prediction is 1, we have to kind of remove the running rate actually for it to be correctly classified for every point here. As you can see here, this trend is correctly classifying it, but if it's classifying maybe this point is passing here, that means we have to, like remove remove a running rate for like we get like this weight and bias minus running rate and we iterate through it, which is like called batch. We have some sort of batch. We keep decreasing until it is correctly classified. So there are some nonlinear data like this. As you can see, we're drawing just a simple line. So for some nonlinear data, actually, you may think, how can I draw a line which separates this data? You can try to draw like this, but you have like some big errors. Error is like how far are you with the solution, because you have to, at the end of the day, generalize in the sense that you have to come up with a solution which is going to correctly classify most of the points here. So this is a kind of nonlinear model. So this nonlinear model, actually, how we solve it is like through the error function. The error function is basically tell us how bad we are doing, and and how far we are for the solution, right? So you can think of error function as like the function which is going to sum up all these errors. Like you have, like if I have this point here, that means it's near the line. That means it have some sort of like big error than this one here. So that means that if you keep like you add the error function and you see how far you are, and you keep like those kind of iteration, adding running rate and adding like removing it for some misclassified point, and at the end of the day you have to have like small amount of error like this, where you can see here it's a small amount of error because like all the points are classified. But if I draw a line like this, that means it's going to give me error like this, too big red and blue. That means that they are misclassified somehow. So there are some discrete vis like a continuous prediction. Actually, that mean, like let's say we are predicting someone get accepted in the university or not. That means we have a discrete, right? So it's yes or no. Someone is classified, someone is correctly classified, it like is going to get accepted or not. Yeah, that's a discrete. But for some function, like for us to do like deep neural network, we have to come up with like a continuous prediction where we say like this person is 30% likely to be late, and 20% likely to be red, and like to be misclassified actually, like and here you can see like it's 60% of likely to be misclassified. Like it's correctly it's not correctly classified, so it have to have like a big prediction. And this is 40%. That means it's misclassified at some point. So this is continuous, like where we come up with like a probability instead of come up like with like yes or no or 0 or 1. So how do we do that? We simply turn like this was step function, which is giving 0 and 1, and you just have to add a sigmoid function or continuous function actually. So this function, it's called sigmoid, which is giving us a prediction between 0 and 1. So it's a beautiful function to use. It's like as you can see the formula here, it's 1 over 1 plus e to power of negative x. So basically the perceptron we have for the first step function is this, like you give it weight and bias, and it gives you like, this is like a perceptron, so it have to come up with like this a step function which is giving 0 or 1, but if you give it to sigmoid, it will have to predict some percentage, like this is 99% to be this, and this is 75%. So the way we do it is like we have this softmax function. As you can see, this we may have so many points, and we have to come up with like a better solution to sum up them, because like we want a sum of the errors to see how bad we are doing. So this softmax function actually is it used like this e to the power of like the given like we want to see like how far, maybe this, we want to see the error of this input actually, like how we are doing with this, and if we want to predict this, so we have to like add the e to the power of z1 e to the power of like the power. That means you have the sum of this error, which can be greater than 1, and for probability you have to be 1. So for it to be 1, that means you have to sum up with it, like to take 1 and divide with the sum, but that we give like a big range of numbers, so we want to diminish it. So that means we have to use e. So this e to the power of z1 and it's summation of e to the power of c1 to n actually. So that if you want to write softmax, I think NumPy has like some useful functions you can extend to, like exponential, that small codes you can write to implement softmax. So again, like if you want to predict like how bad our model is doing, we have to use probability. Like probability, this model is giving like accurate answer. That means like 90%, like this point is likely to be brew 0.6%, and this is likely to be red brew that like is correctly classified 0.2%. That means it's not classified correctly, and this one, as you can see, it have like a low probability. So if you sum up them, like if we do a product of them, we see this this error function, this error, like we have this error of 0.0084. So we have to come up with, like you can see, if we do product, it will give us like a very small number, which is going to be hard to like to iterate through. So we come up with like this cross entropy. Cross entropy actually is for like diminishing like this function, like a function with like a low cross entropy actually is doing bad. That means this is the error function actually. Like this cross entropy does is it takes like a sum of negative logarithm of like these all the probabilities, and it return a sum of it. And as you can see here, as we try to plot these numbers, we get 0.61 here, 1.61 here, 0.51 here. That means like a point with like a very low cross entropy is correctly classified, like has small error, and with a very high cross entropy is like correct, is misclassified actually, or have like a big error. Yeah, cross entropy. Let's say we want to predict if door have like a gift behind. So we have 3 doors. Probability like in the door 1 have like a gift is 0.8. Probability of like a door 2 have like a gift is 0.7. Probability of door 3 have a gift is 0.1. So for us to come up with like a error, like we want to see how bad our model is doing. So let's say we don't have like a gift in door 3, so that means it's 0.9. So which is 1 negative p3. So the probability of like door 3 have like a gift behind. So for the cross entropy, it have to like take the summation of all this, which is like the prediction plus 1 negative y1, which is going to be 0 if like the y is 1, y is 0 here, so y3 is 0 here. That means this is going to be 0 and this is going to be somehow null. So which is going to give a prediction of 0. So if we try to sum up with it, you can see we have like this loss function, like with this error. This is cross entropy if you want to implement it in code. Again, I'll come back to it while training a model. So for the error function, let me explain it bit about error function. Like you have this this function, we have this line, separate the line. So for the error function, you see probability of it being blue is 0.2. Like it's not being blue here, so it's in red area and it's misclassified, so it have to have like a very low probability. So and probability of it being as you can see here, it has like a high cross entropy. As I was saying, cross entropies take it like error, how badly this point is misclassified, and I think like that. So if this is correctly classified, it have very low cross entropy compared to this one. And yeah, if we sum up the negative of the logarithm of like this error, we come up with like a cross entropy, which is kind of error here. So that's what I was explaining in this part. So as you can see, it's a summation of that function we used, a summation of 1 negative y1 ln 1 negative y, like the prediction, and yeah, y ln 1. And so for that come up with like that will lead us to gradient descent. Gradient descent is like how we can like diminish the error. So as you can see here, this is a function. If you have done like multivariable calculus or differential equation, you know these kind of functions we used to plot. So if you are here, you need to to diminish the error. So you have to take step which is taking you down where there is small amount of error. So for gradient descent, it's like you have this for y you have a sigmoid of wx plus b, which is going to give you a prediction. So which is basically this one, wx plus 1, wx plus 2, I put wx plus n, wn plus n plus b bias. And if you want to see how badly you are doing, actually, like how badly you are, like kind of error. If you are here at the point you want to calculate the error and take a step which will like decrease the error. So if you want to take this step, you have to like apply this partial derivative actually. So partial derivative, you have for this error partial derivative, this is running rate. Actually, you have to as we were doing it previously, we removed the running rate while the probability is is negative, and add the running rate while the probability is positive. So for here, but you have to update the weight. So the way you update the weight is through back propagation. Like you back propagate your function and like update the weight. So to update the weight, you have to use partial derivative of all the weights you have actually. So, and a partial derivative of either with respect to weight one, partial derivative of this error function with respect to weights n, and even to the bias unit, for you to get like a better prediction, which would be y prime x plus b prime, which would be better. So I'll get back to it later with a little bit of detail. So the neural network, actually, this was a linear function, as you can see. So, but for the neural network, you can have like this model which cannot be like separated by lines. So you have to come up with like a deep neural network. A deep neural network is a network where you can, like you have some sort of like this node. As you can see here, I have this neuron and this neuron, and it is combining together to make this better prediction. That means there are two linear functions which are combined here. So as you can see at this point, it's 0.8 probability and 0.7 here. If I add them here, by adding them with the weights they have, so it will have to come up with like this prediction, which is going to be here actually, which is like the summation of it. So, and it will have to be plotted here for this function. But again, I'll get back to it. Deep neural network look like again like this. So you may have like even like many layers. Layers is like, this is layer one, this is layer two. Like this is input layer, this is hidden layer. You can have 2, 3, 4, 5. So as you can see, this is passing through, this input is passing through the layer one through the layer two to give the layer three, which is like the output layer. So that's how a deep neural network looks like. You can see it's a combination of these linear functions, which is going to give like a better prediction for nonlinear models. So feed forward, like as you can see, this is a deep neural network. We have input, we have weights, and we have this neuron, right? So this neuron we have to compute and pass the value through here and here and here. So like here we have weights, and here we have those all have like some sort of weights and bias. Bias is this one connected to it. So for us to do deep neural network, we have to do feed forward is basically populating those weight to this neural network actually. So as you can see here, we have like a sigmoid of weight 3 plus sigmoid. It's kind of like a product of a product of this prediction with respect to weight. So for to train a model, we have to do feed forward actually. Like if we happen to do feed forward, we can like come up with like a bad prediction for a model, like it's mispredicting, like misclassifying a point or something. For us to update the weight, we have to do back propagation. This is back propagation. I mistyped it. Back propagation. Yeah, back propagation. You can see we want to like calculate the error. So calculating the error, again, it's like the summation of this. As you can see, this formula is familiar. Like we want to calculate like how badly we are classifying these points, and this point is misclassified. So we want to calculate how badly we are classifying this point, and even the other points which is going to have like a summation of all these errors. And this is the function to calculate the error actually. And if we get the error, we do back propagation. Back propagation is actually like updating the weight and bias. So for here, as you can see, we have error, which is this function, this formula. And if we happen to get error and we want to get error for a specific weight, let's say we have weight 1 here, weight 1, and we want to calculate the way the how badly this the error with respect to this weight. So we have to, like chain rules. And if you want to calculate this, you have to come up with like this. Like you have to do this. You have to come up with this, all the partial derivative of all the weight with respect to it. Like as you can see, we are back propagating into every weight, like every path we pass through, and we have to come up with a sum of it. Again, this is like a math and simple math, you can see, but I'll get through it in the code, which is simple actually. So, and it's a sum of like a product of partial derivative all the way up to this weight 1. So it's a simple one, and if we get the error, we have to like somehow update the weight to like diminish the error. So let me get to the code. Yeah. So this year I'm trying to predict students admission. The data is from this. I'll use pandas, and yeah, if you can see here, like data have like if someone is admitted or rejected, and grade and GPA and rank. So this function is to plot the data. So if you plot the data, you can see people who are rejected and accepted. So it's quite complicated. So, but this is for grade and test. So if they come with like a GPA, I guess it will be somehow easy to plot. Yeah, you can see here if I try to plot grade, test grade for people who have rank, like they have rank 1, 2, 3, 4, 5. If I try to visualize the data, as you can see, this is for people who have rank 1. Most of them actually accepted. Rank 2, it's quite equal, and rank 3, most of them rejected somehow. So, yeah, to do as you can see, we have this data. For our neural network to train, we really have to like do some sort of encoding data, and like come up with like the way we can scale the data and decode it for it to be like, as you can see, we have this gray is like this number is too big for a neural network, and this GPA and this rank you can see is categorical, so we have to encode it like one hot encoder, like as you can see here, the way I did it.
Excuse me for a minute. Could you zoom in a little?
Yeah, sure. Can you see now?
A little bit more.
Yeah.
Yeah, it's okay.
Yeah, for one hot encoder is like the way you can see it. I was trying to encode this rank. It's categorical. So categorical, that means like instead of having 1, 2, 3, 4 or something like that, I have to come up like rank 1, rank 2, rank 3, rank 4. It's like it's better for a neural network to get trained well. So as you can see, if someone have rank 1, it have to have like 1. If it's not 1, that means it's populate 0. That's for one hot encoding. Yeah, for, let me see. To scale the data, actually, like you see, we have gray here. Gray has like some sort of big numbers, and we have to, scale them like for it to be a bit similar to, as you can see, it was big compared to this and this and this. So you have to, yeah, to split it. So the way I split it is like, it's kind of like you have to come up with like a better algorithm for you to, like split it. As you can see, it give me like some sort of like small numbers for me to predict. Actually, it's like for me to use in neural network. Yeah, for splitting data, like you have to split it into like training and testing data set. That's simple one. Yeah, and for data into target and feature. And the target, that means like if I have a target and feature, target is like if someone is admitted or something, or rejected, and if it's not admitted, then it's rejected. Then for features is those features like gray and GPA. So to try neural network, as you can see, we have this sigmoid function here. It takes the number and it returns a sigmoid. That's 1/1 plus exponential of e to the power of -x. So sigmoid prime is like a derivative of sigmoid actually. So it will return like this. The sigmoid have like a better derivative, which is this. And for error function, for this error function, actually, this is the error function I'm talking about. So as you can see here, NumPy did it where like y np log output one negative, which did this pretty much did that formula actually. Yeah, for backpropagation, like you have to return error term for a specific point actually. So this is the backpropagation, which is y negative for binary cross entropy, y negative y hat to x, and for mean square error, you have to come up with this y negative y hat sigmoid derivative of sigmoid x to x. So here I implemented like this binary cross entropy. So to train neural network, you have to have epoch. Epoch is like this number of this number of iteration is going to do like to update the weight and come up with like a better solution. Update the weight, come up with a better solution. And you have to have a running rate. Running rate I was talking about is how, like, which kind of like step, how big this step is going to be. Like if I take like a gradient descent step, I have to have like a running rate telling me like how far can you go. Because if I don't do that, it can take like a big step and try to jump without getting like to local, like the minimum error. It can jump to the high error and something like that. So training a neural network is pretty much easy. You have to loop into like epoch and do, like output. You have to calculate the error and come up with like a new weight and update the weight. Updating, like you have to you loop through epoch and like calculate the error you have right now. And if you get the error, that means you are going to like see how bad you are doing and update the weight depending on the weight you get. And if you update the weight, then you have to like loop through and calculate the error again and update the weights, and it will have to give you like a better prediction. As you can see, the train loss with will somehow decrease. Again, I will share this code, GitHub. So I have to wait. Like as you can see here, I get epoch of like this is 20,000 epoch, and running rate is 0.00001. So you have to take like small steps. So I have to wait for it to get to epoch of 2000. And if we, as we wait, let me see. That's like actually what we are doing. Like we have this error. We at some point you calculate like the error you have, and you have to take a step like to decrease the error. A step to decrease the error is simply like updating the weight and bias. So in your function with respect back, if you have like a deep neural network, you have to update the weight all the way to like the initial weight actually. So, and if you're training, that's what like the back propagation does. It back propagates and update the weight, and like feed forward it, and like get new error and see how bad it's doing, and back propagate and update the weight and feed forward it. It keep taking those steps until to get like a better prediction. Yeah, so as you can see for this epoch, we kind of end up with the weight of 0.61, which is not bad. And if we try to see how accurate using test data, so you can see we are 0.77 accurate, so which is not bad. Somehow good. I don't know if it's helpful. Maybe I can take some question and try to explain them if there are.
We have a question from Olivia. Is it enough to use one perceptron to get accuracy?
No, for perceptron, it's like a simple concept, right? So if you have like a simple linear question, like maybe you have two data, like you have a student grade and student tests, and you have to come up like a simple, if your neural network can come up like a simple linear regression, that's okay with a perceptron. But if your network is quite complicated, you have to come up with a big deep neural network, which is going to be using pretty much like complicated, have to have the input layer, hidden layers, which is going to be again connected, and like giving some prediction. I can say like it's not enough for a simple perceptron to predict well. If you want your model to learn, you have to build like a quite complicated model.
Okay, right. There's another question from Evelyn. What do you base on when choosing the number of epochs?
Yeah, for the number of epochs, it depends on data you have and how you are. I can say that there's no like a specifically you can say like you have to take this epoch, but for some question like imaging, people try, like that's how you fine tune your model actually. Like you try to like increase number of epoch, you try to increase learning rate, to decrease learning rate, see how Barry is doing. And there are some concepts you can come up with, like if you're training a model and you just come up with a big number of epoch, and maybe you want to, like at some point the model we try like the like the error function is going to like increase. So if the error is increasing instead of decreasing, that means you have to like kind of turn off the model where you are it's quite complicated, but you have to like fine tune your model, try to update the weight and bias and running rate. And if you happen to not come up with a better solution, you have to come up with some consider some concept like let me see. A concept like momentum, where you start with like a random weight, but that random weight will going to lead you to local minima. Local minima means like you have like local error, like small amount of error which is local. Let me try to explain it in. As you can see here, we can like try to decrease here and here, and if you start here, you can end up like decreasing here, which is small amount of like big amount of error other than here or here. Local minima is like you started here and decrease here, and if you try to increase, maybe your I mean, your model is trying to increase, and it can increase here. It can't increase here because it seems like I'm increasing like there are some errors, like I'm getting far from the solution. So if you try to like apply momentum, which is actually you start with some random point. I start here, like you can start here, and try to do like gradient descent. You try to see which one is giving like small amount of error, because if you try to a bad point, you end up with local minima, which is like a small amount of error at that point, but it's as big it's bigger than like the general small amount of, like you have some point here, it's pretty small, you can descend to up to here, but if you choose to descend here and the model is trying to increase here for it to descend and increase and descend, that would be a hard time for model. So if you have to drop here saying maybe I get this right, and whereas if you start here and you decrease here, you get like a big to the bottom of your error actually. So I can say to choose like running rate and approach, it depends on the problem, and you have to like fine tune your model, try to play around with it and see how like the one which is giving like small amount of error, and you come up with a better solution on that. Yeah. I guess I think I've answered your question.
Yeah, all right. These are the questions that we have so far. Um, yeah. If anyone has a question, feel free to post it in the chat session. Yeah.
Yep. So let me try to explain another. Yes. Let me try the one which is more visual. Yeah, for gradient descent. So I'm going to try to get to it. Let me learn it. So I'm trying to explain like gradient descent, how it works actually. So as you can see here, we have come up with like just a random weight and like data, and we try to map it into the blue and red points. And for the first, maybe if you come up with like a random weight, we have to draw maybe a line here or here or here. I don't know. Depend on the weight it randomly created. And for gradient descent, it have to like come up with a better solution. Like as you can see here, if I try to learn, it's pretty much the same as the neural network I built there. But as you can see here, as I try to decrease, it is like trying to draw this line, which is correctly classifying a point. And maybe it started like this and tried to decrease and decrease and decrease up to here. As you can see here, it's giving like a better view of how neural network works. Like it starts here and it decrease or increase way depend on like how bad the point are classified and stuff like that, and start to try to draw a better line to separate them. As you can see, weight have to like error have to diminish. So at some point, if you train a model, it will have to be like overfitting. So if it overfit, that means the error will start to increase for testing data. Like you have a training data, it will keep decreasing because for training data you are giving the answer, say like I want you to be specific to this, I want you to be specific to this, and for it, if the model overfit, that means it's memorizing instead of generalizing. That means if it memorized, this point have to be blue. So if anytime you give it the point which is near this, it is not going to take it because it draws like a small line here for this point. So if you don't be specific to this point and maybe put it here and put it here, it is going to say maybe I don't know that, or it's the point is red, which is crazy. So for you to train a model, if you see for testing data, here I don't have like a testing data part, but for testing data, for training data, it will always decrease because you're giving it the output, but for testing data, it will start to increase actually, like the error start to increase instead of decrease. That means the model is somehow memorizing the training data and it can't like generalize for the testing data. So that where you have to like turn off your model, depend on like the NF epoch you're on, and like say maybe on this epoch I see the testing data start increasing and I have to stop here. That means this number of epoch is good for me for this model. I don't know if there is any other question. Again, I will share it on GitHub. Yeah, I'll share it on GitHub actually. After this session, I'll try to push the code, and for this neural network repository, I'll share the code, and it includes like some prescription on how to like install the module. And yeah, I think I'll push the code and I'll share it right. The other, what is the solution boundary is correcting? I don't know if I'm getting you well. If you are talking about this solution boundary, actually, like you have this data and you want to correctly classify them. Correctly, that don't mean like you have to be 100% correct. So as you can see here, it's quite complicated to be 100% correct. But if you draw down here, that means you have like a small amount of error. At some point I misclassified, that's okay. But if for here boundary solution boundary is like, you see this is the line we predicted after training our model. So after training model, it come like way back from here, like trying to draw a line, trying to see how bad it's doing, and it come up with this better line. Actually, you can see it's correcting this. Like we have this data, we want to separate them correctly. The red point here and blue point like in the other part. So this line actually it's the model. That's what we call model. If this like a deep neural network model. So if you come up with like another point, if you are testing data, and maybe the point is here, it will have to correctly say, yeah, this is blue. And if you come up with like a point here, you have to say this is red. Yeah, and for I guess this neural network concept is quite like the basic fundamental for deep learning and deep reinforcement learning. Except that deep reinforcement learning, like they use like Q tables, not actually like real data. Q table is like you're taking like a random action and you see the outcome and you try to map up in the table and you try to do a neural network which is going to learn from it. And for here, for deep learning, it's like you have data, like supervised, and you have data which are labeled and you feed it to neural network. Neural network try to learn the data with respect to output you are expecting, and try to like come up with a solution which is generalizing the problem you're having. If it's classifying image, if it's like see if the student is going to get accepted or not, and like come up with a better solution for you. If you populate the data for the future, maybe you can make it even like an endpoint. If you hit an endpoint with those data, it have to predict you, I'm saying this student is going to get accepted or rejected. It's kind of fundamental, and if you don't have like to memorize all these mathematics, and we have like better libraries like TensorFlow and PyTorch, which are like they simply do it. Like you have to say like model.train or stuff like that, and does all the mathematics behind and give you the output. But it's better to have like a fundamental understanding of how neural network work. Yeah, I guess there is no other question.
No, there's no other question.
Yeah. Yes, that's it. I, I, I think we can end it here. Thanks for having me, and yeah, I'm glad you guys learned a thing or two.
Thank you so much for today's session. Evelyn is asking about the GitHub link. Once you push it, you can share it through our email or the Twitter account, and we'll share it to the rest of the community. And again,
Yeah,
thank you so much. Thank you so much for showing up today. Yes.
yeah. Thanks for having me. Bye.
Bye. Have a great time.
Yeah.